Hello everybody, this is 2021 AIME I Problem number 11, I should say, and this is a geometry problem. Here's a view of this problem. We are given this cyclic quadrilateral with side lengths 4, 5, 6, and 7. I might as well just go ahead and start with a nice drawing, as nice as I could. So we have our quadrilateral with 4, 5, 6, and 7. There we go. A, B, C, and D. Yeah, well, I'll just go ahead and put the lengths as well on the picture. We are told that, okay, we're going to go ahead and also construct these points A1 and C1, perpendiculars from A and C onto BD. Let us go ahead and use blue color, why not? Or let's keep that same color. All right, so colors are important, right? So more colors we work with, it's easier to identify the regions and stuff like that. So we want to have perpendiculars from A, oops, that's a 90-degree angle, and C, oops, those two blue lines are parallel, I suppose. And similarly, we'll do the same business from B and D as well. Let me just go ahead and mark that later on. Hold on. So we have a 90, okay, so pretend this is 90 degrees and there's another 90 degree right here. So this is A1, that's B1, C1, and we also have a D1, right? Something like that. Whoops, this is D1. The question says, as it is, we need to find a perimeter of A1, B1, C1, and D1. Okay, let's just go ahead and draw that picture as well. Which color? Why not? Red. A1, B1, oops, that's a tiny, C1, D1, oops, there we go. Okay, so that's the quadrilateral of interest, A1, B1, C1, D1, inside ABCD. I might probably need this shape again later on. I might regret like messing up with the picture. So from the beginning, I'm going to go ahead and duplicate it and move a copy just down below, just in case I need it. I can go back to the original picture, but this is the original picture before I mess it up. What can be done? To find the perimeter, we need the side lengths, A1, B1, C1, D1. Inspecting the picture, we see we can make a couple of observations, I suppose. One of which is, I guess, when you saw this. Okay, so let's list them actually. What kind of observations can we make? For instance, it's not hard to find the area of ABCD. Do you see why? Area ABCD of ABCD is easy. Why? By Brahmagupta, which is, I suppose, a 7th century Indian mathematician. Interestingly, he was able to formulate the area of a cyclic quadrilateral. In this case, ABCD is given to be a cyclic quadrilateral. And the formula is, in case you are curious, it is this. At the end of this video, I'm going to sketch a proof of this. I don't want to do it in the beginning of the video because then it's kind of like a distraction. So the square of the area is S minus A, S minus B, S minus C times S minus D. All right, where S is the semi-perimeter of that cyclic quadrilateral, ABCD are the side lengths. When you look at this formula, by the way, what does it remind you, right? It does remind us of Heron's formula for the area of a triangle, and not surprisingly, the proof of Brahmagupta follows from Heron's formula. All right, so this is one observation we make. A second observation, I guess, we make just immediately is all these right angles. A lot of right angles, at least 4 of them, right angles. And whenever you have a lot of right angles, I suppose it's easy to find cyclic quadrilaterals, right? So implies the existence of some cyclic quadrilaterals. For instance, I think not at this point it's just a simple angle chase matter, but for instance, angle BB1C is a 90-degree angle, as is well, BC1C. Do you see that? Both BB1C and BC1C are 90 degrees, suggesting that BB1C1C is cyclic with BC as the diameter, right? So BC is a circle. Do you see that? Okay. So whenever, okay, let me write it like this. BB1, that's a B, believe it or not. BB1, C1C, this is cyclic. In fact, let me just go ahead and draw that circle. If not, why not, right? I have a copy of the picture anyways, just in case the picture is really terribly messed up. I can always go back. By the way, like I said, BC is the diameter of that circle. Do you guys agree? Because of those 90-degree angles subtending the diameter. All right, so this is a horrible circle. But by the same reasoning, angle BA1A and angle BB1A are also 90 degrees, suggesting we have another cyclic quadrilateral right here. Oh gosh. Okay, so my drawing, not the best, but you guys get the idea. So now we are saying that BA1B1, BA1, B1A is also cyclic. But by symmetry, you now see what's going on, right? I suppose AA1D1D is also cyclic because angle AA1D and AD1D is also right angles, right? So, yeah, so this is, I think, very obvious from the way the shape is given. So we have those cyclic quadrilaterals. So we said AA1, D1D. And finally, the last one is probably the fact that DC1C and DD1C being 90-degree angles. I suppose we have this cyclic quadrilateral over here as well with diameter DC, right? So last one is DC1, D1C. DC1, D1C is also cyclic. So all four of these quadrilaterals are cyclic. And whenever you have, so far we have 5 circles, including the circumcircle of our quadrilateral, cyclic quadrilateral ABCD. Whenever you have a lot of circles in a figure, that's very good for angle chasing, especially for those of you who are preparing for Olympiad Math, or at least at the junior Math Olympiad in the US. That's one of the skills that you should be practicing a lot in terms of preparing for those exams. The problem is, like you can imagine, we have so many circles, everything is mixed up, right? So this reminds me of quite a few USAMO problems, I think. Yeah, so that's the challenge of this problem. So how do we navigate through all these angles? If you have some gut feeling about the quadrilateral of interest, which I suppose from the beginning, I guess you guys had might have some feeling about this quadrilateral being well, cyclic or being similar to another quadrilateral and things of that nature, right? And your gut feeling would be correct. It's just a matter of just pursuing the right angles. So for instance, let me just do a little bit of angle chase for you to establish that I claim that A1, like this quadrilateral in the middle, A1, B1, C1, D1 is cyclic, which is one of the first claims that you can make. Let's prove it synthetically. A1, B1, C1, D1 is cyclic. All right. And then later on we will notice that not only it is cyclic, but it is similar to the original quadrilateral, but that's another step. So for the time being, let's see if we can quickly go over the idea of a cyclic quadrilateral. So we need to chase some angles. I don't know, so maybe I can just make sure the picture is a bit larger so you guys will have a better view. So the key idea of chasing angles when you have a bunch of cyclic quadrilaterals like this is to navigate between circles, right? So you should be able to transition from one circle to the next and so on. All right, so if you want to, for instance, show that A1, B1, C1, D1 is cyclic, for instance, one way to do it would be to show that if I can show A1, B1, this is a B1, by the way. Yeah, the angle disappeared. So one way would be to show that, so let me write it here. For instance, if I can show A1, B1, say D1 is equal to A1, C1, D1, then that would be sufficient to establish that this is a cyclic quadrilateral. So let's start with A1, B1, D1 then. If you start with that angle, which is hard to see, but somewhere here, do you guys see that? So this angle over here, A1, B1, D1 is the same thing as A1, B1, C, right? Those are the same angles because B1, D1, C are collinear. A1, B1, D1 is the same thing as, let me go ahead and add the steps here. So that's what we wanted to show, right? So let's move it down below. Let's see after finite number of steps if we can reach to that point. So A1, B1, D1, the same thing as A1, B1, C. But A1, B1, C, if you trace it, okay, as you can see, I'm myself confused. I need to check the angles. Okay, yeah, I can see it. Hold on. Yeah, so A1, B1, C. Well, yeah, I guess. This way is not useful. Okay, I have a better way. Do you guys see that A1, B1, D1 is the same thing as, because A1, B1, D1 is an external angle on the cyclic quadrilateral AB1, A1B, on that one. So as a result, that angle is the same as this angle over here, AB B1. Yeah, I'm pretty sure of it, AB B1. But then AB B1, I'm not sure of it. I'm pretty sure of it. Come on, AB A1 I should have said. Sorry, AB A1. Yes, ABA1. But ABA1, now that's the good deal. Okay, ABA1 is the same thing as ABD. Aha, ABD. But wait, ABD and ACD are congruent angles because they subtend the same arc on the cyclic quadrilateral ABCD. So this is the same thing as ACD. And now ACD, so this angle, is the same thing as, if you focus your attention this time on this green circle, CD1, C1D, you will realize that that's the same as this one because it's an external angle over here, right? Opposite angles add up to 180, so 180, so as a result, so this angle is 180 minus this angle at C, so therefore the supplementary angle should be this one. Yeah. Okay, so that makes sense. All right, whew. So we started with this angle and now we established this. Yay! All right, so what we did so far was, oops, let's just now go back to the original size, I suppose. Oops, let's lock it as well. Okay, so now that we have established that A1, B1, C1, so this is established, this is cyclic. A next step would be, okay, but that's not sufficient for us, right? So we want a little bit more than that because we want to measure the length of this quadrilateral, cyclic quadrilateral A1, B1, C1, D1. And at that step, you start suspecting that, hey, is it more than that? And yes, so what you can do is, we already started doing a little bit of angle chasing. Why don't we just actually, okay, let's just go ahead and finish it. So for instance, so far, this part, okay, so I don't know if you guys can see it, let me show it here. So this portion of angle B is the same as this portion of angle B1. Let's check the remaining portion, right? So for instance, we have a remaining portion, oh gosh, which color should I use, right? So even these colors are not enough. Okay, so let's use black color. Let's see if this angle measures the same as the remaining piece, which is this part. Do you guys see that? If those two measures the same, then I'm good. So I'm thinking of C1, B1, D1. Well, wait a second. So first of all, because we have a cyclic quadrilateral, that's the same as this angle. So C1B1D1 is C1A1D1. C1A1D1 is let me think about it. Yes. C1A1D1 is the same thing as, okay, let's make it smaller again. C1A1D1 is the same thing as DA1D1. It's the same thing. C1A1D1, DA1D1. But DA1D1 on that green circle, this one, is the same as DAD1. Aha. So that's also the same. But wait, DAD1 is the same as DAC. On that blue circle, DAC and DBC are congruent. Whew, all right. So now we have, so the two pieces of the blue angle. So if you look at angle ABC, we established that that's the same thing as A1, B1, C1. We could have done a similar arguments to establish all the rest of the angles. So not only A1, B1, C1, D1 is cyclic, but now we have, in the second step, we established that the second claim as well is proven. The second claim proven is that the circle ABCD, the cyclic quadrilateral, I should say, is similar to the cyclic quadrilateral A1, B1, C1, D1, right? Both of them are cyclic, but moreover, furthermore, they are also similar, right? So you can put a sign of a quadrilateral, even a circle around it. So both cyclic quadrilaterals are similar cyclic quadrilaterals. So now we know the perimeter of one of them. So if I know the ratio of similarity between these two quadrilaterals, I can easily find the perimeter of the second quadrilateral as well. So how can I get that ratio of similarity? Well, when you inspect the picture again, which is, like I said, already pretty messed up, but you guys, I think, okay, so let's dive deeper again into the picture. Unfortunately, we need to keep doing that back and forth. So by now we know that there's a relationship between B1, C1, and BC, right? So that's the whole point. So I want to find that ratio, the ratio of B1, C1 to BC. So how can I find that ratio, right? So that will give us the ratio. So check this out. So how about this? You just realize that, so for instance, this, the diagonals intersect. Let's say that the diagonals intersect at that point P. So this yellow triangle B1, PC1, because we have a cyclic quadrilateral, clearly is similar to this yellow triangle. Do you guys agree? Those two triangles are similar because, for instance, a triangle B1, PC1 and BPC are similar simply because angles C1, B1P and CBP are congruent. And so on, right? So similarly, angle, let me put a mark here. So this angle is associated with this corresponding with that angle. So those two triangles are similar. But then that's exactly what we need, right? So the ratio of similarity, for instance, B1, C1 to BC can be expressed as B1P to BP, for example. Do you guys agree? So this ratio is, at the same time, by using those two similar triangles, is the same thing as B1P to BP. But how does this help? Well, it helps greatly because now if you change perspectivity yet one more time, focus on this red triangle. I don't know if you guys can see that trick that I'm about to pull here, but this is a right triangle. So I'm talking about right triangle BB1P, where there's a right angle at B1. So the ratio of B1P to BP is really, if you label the angle between the two diagonals, so for instance, theta. So do you guys agree that if angle B1PB, B1PB is theta, then it's just the cosine of that angle, cosine of angle theta. Does that make sense? And that's it. So therefore, we establish that the ratio of similarity between the quadrilateral ABCD and that little quadrilateral A1, B1, C1, D, it's just nothing but the cosine of the angle between the two diagonals. Now the problem boils down to calculating that angle. How can we calculate that? Well, the good news is we can calculate the area of our quadrilateral in two different ways. One would be to use Brahmagupta's formula, this one. There's a second way, a very easy way to also calculate it based on using the length of the diagonals. I don't know if you guys remember that, but the area, let me write it out like this, the area of our quadrilateral will end up being just the product, half of the product, AC times BD times sine of angle theta. And you guys can imagine where this formula is coming from as well, right? We've seen this formula previously in calculating the area of a triangle. So area of ABCD are cyclic quadrilateral. This formula, by the way, works regardless. It doesn't have to be cyclic. We can split it into four triangles: APB, BPC, CPD, and DPA. Each triangle, we can calculate it using the area of a triangle, which has the same format. Add the four of them and combine them, it will give you this formula. You might say, wait a second, I don't know the length of the diagonals. How in the world am I supposed to find their product? Well, the good news is yet another result that we know is because we have a cyclic quadrilateral, we can benefit from Ptolemy, right? Ptolemy theorem. Ptolemy, on a cyclic quadrilateral, the product of the diagonals, in this case AC times BD, is simply the sum product of opposite edges, right? So 4 times 6 plus 5 times 7, which is 24 plus 35, I suppose 59. So now coming here, 1/2 times 59 sine theta. So that's one way to calculate the area. Second way would be to use that formula that we mentioned. The semi-perimeter is just the sum of all these side lengths. So we have 4 plus 6 is 10, 5 plus 7 is 12, 10 plus 12 is 22, half of it is 11. So therefore the square, there's a square here, of the area, which means the square root. So this expression must also be at the same time. So the semi-perimeter we said was 11, I suppose. So we have 11 minus 7, 11 minus 4, 11 minus 5, and 11 minus 6. That's it. So, and this is, you guys can easily solve this for sine of theta. I think if you do the algebra, sine of theta comes out like this. And you can follow this proof also in AOPS. So sine of angle theta, the angle between the diagonals, is equal to 4 square root 210 all divided by 59, after which you can build an artificial right triangle, or you can use the identity sine squared theta plus cosine squared theta equals 1 to further establish that cosine of theta, the angle between those two diagonals, measures, the cosine of that angle measures 11 over 59. And now finally, because this cosine happens to be the ratio of those corresponding sides between those two similar quadrilaterals, we can do the following. So because B1P is simply, if you do cross multiplication here, so B1P is just BP cosine theta, we can factor out all those terms. So we have the following at the end, right? I should say this one, sorry. Use this one. So cross multiply this with the cosine theta, we would get B1C1 is cosine theta times BC, right? So therefore, the question is asking for A1B1, the perimeter, plus B1C1, plus C1D1, plus D1A1, which is simply, like we said, AB times cosine of the angle between the diagonals, BC times cosine of the angle between diagonals, and so on. CD times cosine of theta plus DA times cosine of theta. We can factor out cosine of theta, plug in its value, which is 11 over 59, and then the sum of AB plus BC plus CA plus CD plus DA. But we already know those lengths, so that would give us 11 over 59, AB 4 plus 5 plus 6 plus 7. You add up these values, which was 22. 11 times 22 is 220 plus 22, 242, 242 divided by 59. I don't think this simplifies any further, so that's the desired perimeter of the quadrilateral created, the A1, B1, C1, D1 quadrilateral. So this is the ratio. The question is obviously asking in that same spirit the sum of m plus m at the numerator and the denominator. So in the spirit of AIME, 242 plus 59 is the answer, which is, if you add them, I think you get 301. All right, so like I promised, so that's solves the problem. One thing, I'm sure everyone have seen Ptolemy theorem previously, and you guys can also think about how to prove it using similar triangles, I suppose. Let's briefly talk about this formula. Brahmagupta formula, which applies only to cyclic quadrilaterals. So where does it come from? The way the formula is presented, it seems natural that it comes from Heron's theorem, right? So what is the idea? Well, the idea is this. So if you have this cyclic quadrilateral, let's say you have A, B, C, D. The idea is the following. So you guys can just complete into a triangle. So you just extend two of the sides of this cyclic quadrilateral, let them meet at a point P. Wait, you might say, wait a second, what if those 2 points don't meet at P? So if none of the opposite sides of this cyclic quadrilateral meet at such a point, it means your quadrilateral is a rectangle. And if it is a rectangle, it is just a simple matter to confirm that this formula is regardless true, right? Because the semi-perimeter in that case would simply be A plus B. The side lengths would be AB, AB, and plug it into the formula, you will see that the area will come out as A times B, as expected. So anyhow, so we don't want that special case. So one of the pairs of opposite sides should meet, and we did such. You guys would remember that this leads to similar triangles. So this angle is congruent to this angle, and similarly this angle, because we have a cyclic quadrilateral, is congruent to this angle. So that gives us the idea that obviously from this angle chase, we can see that triangle PAB is similar to triangle PCD. So therefore, the ratio of their areas will be also corresponding with each other. So for instance, well, let's label these sides A, B, C, D, for instance. Do you guys agree that the ratio of those similar triangles is A to C? Do you guys agree? So as a result, the ratio of their areas, PAB to PCD, must be A squared to C squared. But wait a second, PAB to PBD, let me do it the other way around. A squared to C squared is equal to, but PAB to PCD, let's keep the PCD. I like that because I'm gonna use Heron's formula here. But I can express PAB as the difference between PCD and the cyclic quadrilateral whose area is the area I want to compute. So therefore now that makes sense. PCD, okay, so now the steps of the proof. Step one, calculate the area of PCD using Heron's formula, which requires its own proof, I suppose, but I'm sure you guys have seen that formula previously. Step two, we establish some similar triangles. So using similar triangles, so for instance, let's call this one as U and V. Find some relationships involving U and V as well, because that will be part of your side lengths of your Heron triangle PCD, right? Similar triangles like the similarity that we established earlier, similarity ratios to find U and V in terms of ABCD. Alternatively, you could have used power of a point, so that would lead you to the same result anyways. And that's it. And then combining everything together. Step 3, combine them into let's call it star. Combine step 1 and step 2 in star expression. That's it. So if you follow these steps, it should be a straightforward matter to just prove that result, that huge result for cyclic quadrilaterals. Apparently, ABCD, the area is simply the square root of S minus A, S minus B, S minus C, and S minus D, only if ABCD is cyclic quadrilateral. And that's it. That's all I have for this video. Hope you guys enjoyed it, and looking forward to see you guys in another lecture. Bye.